Hi everyone, welcome to the lecture number 3. So as we have talked before, now I will start doing these lectures online. I'm going to post them online, so I'm recording them now, and I'll also be posting the lecture notes. So if you have any questions, you can ask me at the beginning of the lab each week. Okay. What we're going to talk about today is something called random uncertainty. Okay, and as we have discussed last week, uncertainty can be defined in two ways, or it has two parts to it. One is the instrument error. Okay, and then the other one is the random error. Okay, instrument error is basically the design stage uncertainty that we discussed last week, and it comes from the fact that the instruments that we use are not perfect, and there's certain inherent errors or uncertainties associated with them. Therefore, there's some uncertainty in our measurements. Random error, on the other side, right, comes from inherent variations of the method by which that we measure things. Okay, so what I mean by that is that, let's say we have start working. You start working in a factory, right? And then the factory makes ball bearings. Okay, and ball bearings, I don't know, you maybe generate 1 million a year. Okay, and then the factory says that, well, we want to know what is the size variation or the weight variation, right, in our bearings, because we want to, hit certain standards, and you're tasked to measure that. Okay, let's make the assumption that the bearings that has been generated by that factory for each year is a bag of bearings. Okay, obviously this is a big number. Okay, and then as an engineer, your task is to understand or sample some of these bearings, right, out of the bag, and make a determination. Okay, what is the expected range of size or diameter, whatever, of those bearings, right, out of the factory floor. So let's say, for the ease of understanding today, we pick 10 bearings. Okay, and that 10 bearings is really called my sampling. Okay, so I've sampled 10 bearings, and sample size is usually denoted by n. So basically, I had a sample size of 10 for my measurement. Okay, and those 10 bearings then are going to form my data set, right? Because that's my data that I have collected. Okay, and then I'm going to perform my measurements. Okay, and then I will measure the average value, right? So the average of my 10 samples, which is x bar in this case, because it could be anything. So it could be diameter, right? Or it could be size, weight, and so on and so forth. Okay, so doesn't really matter what they are. So the errors associated with the measurement itself, right, is the instrument error, right, and that goes back to my design stage uncertainty. And for today's class, okay, for today's discussion, let's assume that design stage uncertainty is 0. Okay, so that means that let's not think about the design stage uncertainty. Okay, and then the errors that are associated with my sampling in data set are the ones that that form the basis of random error. Okay, why? So let's think about that, right? So using statistics, what I am trying to do, okay, is I want to get to an estimation of x naught, which is the true value, right? And that's basically, let's say that's the number of bearings that has been produced, or the diameter of number of bearings that has been produced by that company for that entire year, okay? So it's not realistic that I will be able to do that, right? So therefore, I have sampled 10 bearings, right? And I would like to estimate then, based on that value, a mean value of my sample mean, right? And then I would like to estimate an error associated with that, right? Ux at certain confidence interval, okay? Again, for today, let's assume that just ignore the fact that this comes from design stage uncertainty and random errors. We are not going to talk about design stage uncertainty, but sort of focus on the random error aspect of it, okay? So first part of the random error, right, that's important is that if I pick 10 samples, okay, I will reach to a mean value, okay? And if I take another 10 samples, right, I might end up with a different mean value, right? Because that it's just random sampling, and I wouldn't know what that would be, okay? So basically, random error comes from statistical fluctuations, right, that comes from my sampling, right? Or it can be affected by my sample size, right? So basically, if I only have selected, let's say, 3 samples, and 2 of them were at the other end of the spectrum, like maybe something was faulty and those 2 bearings was right next to each other, right? And I come up with like a sample mean x1 bar, right? Those, maybe one of them say was bad, right? But since I only have 3 sample measurements, my mean was heavily affected, right, by that one bad bearing, okay? If I have measured a n of 100, even if my, that will lead to another mean, x2 bar, right? But maybe 10 of them were bad, or not up to specs, but my measurements were less affected by that 10 bearings, right? Because of the fact that I measured more samples. So ideally, as the sample size reaches to infinity or to the population number, right? Then I will be closer, right, to the true value as much as possible. So the idea there is then you want to sample as many samples as you can to get a better estimation, right, of the true value. However, it is not always possible, right, because we will be unable to do that based on time, right? Maybe for bearings, right, it might be easier to measure, but like for more complex measurements, right, or maybe complex characterizations, time or money may be limiting. Therefore, you're going to have to rely on small number of measurements and do the best you can. We cannot, however, change the sample size every time, right? Or increase our sample size all the time. So we rely on something called the central tendency, okay? Tendency. So central tendency theorem says that samples or the average of the samples, right, tend to sort of coalesce into a mean value, right? And we could detect that, right? For example, if you have a dice, right, a six-sided dice, right? Like say 1, 2, 3, 1, 2, 3. Here's a dice, right? Six-sided dice. And then if you were to die that, the probability that you're going to get a number between 1 and 6 is 1 and 6, right? Because you have equal chance to have, equal chance to get each number. If you were to have two dice, okay, let's make it two dice, then what happens, right? So the chances of you getting number 7 increases. So if you were to plot the probability of possible numbers on the probability of numbers that you can get, right? Probability versus the numbers, right? So that will be starting from 2 to 12. Let's say 7 is the middle. And if you look at the probability, you'll find that it actually maximizes at 7. The reason is that at 2, you only get one configuration, right? That can be 2, that's 1 and 1. And at 12, it's the same thing. You can only get one configuration, that is 6 and 6. But for 7, you can get 6, 1, 5, 2, 4, 3, and so on and so forth, right? So that means that the two dice system has a central tendency to get to 7. Okay. Let's do an example of this. So, for example, we again had the ball of bearings, right? And I wanted to know what their diameter was. Okay, so I have decided then, let's pull out 20 ball bearings, right? And I measured their diameters, right? Say with the caliper or something else. And let's put a scale here. Okay, I'm going to divide this to a couple different intervals here. It doesn't matter what the intervals are, okay? And then let's say I've been measuring, right? So I measured and then I found 1 come to this interval, 2 come to this interval, 4 come to this, 5 come to this, 2 come to this, and 1 come to that, right? Something like that. Okay, so then we can visualize this in a graphical form called histogram. Okay. Okay, and a histogram is basically means that if I measure a value n times, or say 20 or 10 times, right? Histogram is defined as the graph of how many times a measurement, right, falls within a certain interval. Okay, let's measure. Let's define some definitions here. Okay, so this is a k interval. Okay, and the measurement value n is the sample time, sample number. I'm sorry, sample number. And then the other one, the thing I want to say is that the each measurement is called xi, right? Okay, so then the number here is going to be defined by nj. Okay, this number is the number of times right, xi, okay, falls between a certain k interval. Okay, so if I were to count these based on my measurements, okay, let's look at my first interval. How many I had? I had 1. In this one, I had 1, so I'm just reading it from here. And then in the second interval, I had 2 samples. And in the other one, I had 1, 2, 3, 4. In the last one, I had 1, 2, 3, 4, 5. 5 of them. This one I had 2. Okay? So that basically tells me what was the distribution of samples that I had in my measurement. Okay? So there are certain rules that we can use to determine how many intervals, right? How do you decide how many k intervals that you have? So a good estimation for a k interval is the Band-Pearson estimation. It says that the k is defined by 1.87, okay, n minus 1 times to the 0.4, okay. This is for small sample sizes, but for large sample sizes, you can estimate it as n over 1 over 2. So it's the square root of n, okay. So let me go to an example and do this on example, okay. So because that will be so much easier for you to deal with, okay. So let's say, let's open our example screen here. Let's say I had 20 measurements, okay, here, number 1 to 20. And then I have xi measurements, so those are 0.09, 0.108, all that. So that's my number of measurements that I had. So I've listed some of the things that I'm going to do here. Number 1 is the number of samples, that was 20, right? And then I also look at it graphically here. So that's my range starting from 0.6 to 0.4, and I had more samples sort of fall into that range, and then less number of samples fall into that range, okay? So when you do the histogram, it looks something like that. It says that the number of intervals that I should use, right? I've calculated by 1.87 times 20 minus 1 times over 0.04, and I think I missed this here, it's plus 1. Okay? So then I'm using this estimation here. Okay? I have come up with the estimation of 7, okay, and then I've divided to 7 integrals or 7 different bins, and I've counted how many times a measurement fall into that bin, right? So it turns out that this bin had 1 sample, this bin had 3 samples, this bin had 4, this bin had 7, this bin had 2, this bin had 2 as well, okay? So to do that actually in Excel, I have a video in the YouTube that I will put the link to, and you can figure out how to make this histogram based on that. Okay. Let's close this example for now and go back to our lecture. Actually, one thing I wanted to also show is that, let's bring that back up. I wanted to show the probability estimation differences between the Band-Pearson and n over square root of n estimations. Band-Pearson here is the blue, and then the square root estimation is the orange. You can see that for about, say, 500 samples, right? These two track together very well. However, the estimation of n square root underestimates a little bit. You can see that it's a little bit lower than Band-Pearson, right? But then it starts overestimating it. So basically, rule of thumb is that if n is sample size is smaller than 500, you use band.pearsall. If it's over 500, you use the estimation of n. Okay, so that's how you use it. Okay, so now let's close this example here and then go back to our lecture and continue on. Okay, so you have probably noticed that in our example that the sample distribution was somewhat of a bell-shaped curve. Okay, so I'm just going to redraw an ideal one here. That's not the same one that we draw, but let's say this is a histogram. Okay, these are your bins, and then this is your NJ. Okay, so you have noticed that this looks like a bell-shaped curve, somewhat. Okay, probability densities, as far as the probability densities goes, these densities can be a normal distribution, okay, or it could be things like log normal, right? For example, if it's skewed on one side, okay. For things like mechanical testing, right? These things can be log normal. For example, if the samples are breaking at one particular, load, if you do the distribution of that, you can have a log normal distribution. But in this class, we will only deal with normal distributions, and we will assume everything has a normal distribution. Okay. Okay, let's think about what the normal distribution is and where does it come from. Okay, to do that, we will go a little bit back in time and talk about your 360 class and maybe a little bit get into z-scores. Okay, the normal distribution tells me that what is the probability of distribution, right? The distribution probability of things within that population and where they should fall in, right? Based on that distribution sort of function that you have, okay? So let's assume for now that you know the entirety of the population, okay? Let's say you measured all the ball bearings in that bag that we've been talking about, okay? And then you're able to measure every single ball bearing there. So therefore, you can tell that you have access to the entire population, okay? So let's assume that's the case. Then a normal probability distribution will give us some power in understanding what is the probability of samples being in a certain range. So what I mean by that, so okay, let's do some example for that, and then you should be able to deal with it. Okay, so let's say for a fully characterized and fully known population, okay, a normal probability distribution, okay, is defined as 1 over sigma times square 2 pi, okay, exponential minus 1.2 times x minus x naught, which is the, we're going to get there. Let me write it down. Okay, so some definitions. X naught here is called the true mean. Okay, since we have measured all the ball bearings in that bag, then we know what the true mean is, right? And then we also know what's the true variances, right? Because we actually know what the variance within that bag is, right? And then we also know, what the population looks like, but also this px function, right, is maximum at x equals to x naught, right? Because that's its central tendency point. So if I were to draw this, you'll see that you'll have a normal distribution, okay? And then at the center of it, going to be x naught, right? Because that's the true variance, the true mean, okay, of x. Maybe I'll just write that. It's true mean of x, okay? And then this then becomes my probability distribution, px, okay? So what I'm trying to figure out is that, say, if I know the entire distribution of this, then I could say, what is the probability of a measurement being x naught plus, say, delta x, and x naught minus delta x. And basically, if I know the entire px distribution by calculating the area under the curve, I can figure out what is the probability of measurement being in that region, okay? If I were to write that as an integral form, okay, it will look at this like this. So I'm going to change the x to these ranges, right? That will be x naught minus dx x naught plus dx, okay? And then that will become an integral form. That's going to be dx, and that will be x naught plus dx. That's x naught, okay? Then that will be px dx, okay? So if you were to define a couple things here, okay, to solve this integral, I'm not going to go over the entire solution, but if you have any questions about it, we can do it later on. So let's define a couple things. Beta is going to be x minus x naught divided by sigma, okay, so that's going to define as beta. Z1 we are going to define as the integral, the interval that we are looking at, dx over sigma, okay, and that's also equal to x1 minus x naught, okay. The names for these are, this is called the standardized normal covariate, and that's called the an interval. Okay, so then the solution of this integral, right, is going to be that if p is going to be within minus z1 plus z1 is going to be given as 2 times 0 to z1 okay. So this solution is given at table 4.3. So here's my normal distribution of probability. Okay. Here's my central tendency point. Okay. So when z equal to 1, okay, this is z equal to 1, okay. What was z? Z was an integral point, or just like a sort of like an interval divided by variance, okay. And that means that if z equals 1, then the delta x is equal to sigma, yeah. So that means that this becomes x naught okay, plus sigma, and that's going to become x naught plus 2 sigma, and that's going to become x naught plus 3 sigma, okay? And the same thing can be written here. That's going to be x naught minus sigma, x naught minus 2 sigma, x naught minus 3 sigma. Okay, so what is the significance of this? Okay, let me show you. So if you are within the first standard deviation, is z is 1 here, okay, so that's your 68th percentile. Okay, if you do sigma equal 2, z equal 2, let's draw it here. Okay, then this is your 95 percentile. I keep saying percent, sorry. 95 percentile. And the last one, let's do a different color, is going to be your 99th percentile. Okay, so what is the significance of this? So the 68th percentile means that there's a 68% chance that a measurement of x will have a value within that interval. X naught plus sigma, x naught minus sigma, okay? So let's think about the implications of this, okay? So if this is something that we use every day in clinic, okay? So in clinic, when you are, say, 55 years old and up, you are asked to do a bone scan, or other means DEXA scan, okay? So the DEXA scan is recommended by clinicians, okay, of ages 55 or up, okay? So that means if you are 55 years old or 50 years old, that chances are you are going to get a DEXA scan every year, okay? And we were doing this since maybe 1930s, okay? So that means we have scanned millions and millions of people, okay, through this scheme. Then we have a pretty good idea of what the DEXA scan of the entire population looks like, okay? And lo and behold, it's a normal distribution, okay? So there's a mean central tendency number, right, of that population. Even more interestingly, female have a different central tendency, males have a central tendency, Asians have a central tendency, or African Americans have different tendencies, so on and so forth. Okay, but let's say within a population, let's say white males, okay, then you are going to get a DEXA scan, okay, and then the doctor, okay, is going to give you a z-score, okay. So if your z-score is 1 or lower, that means that you are within the 68th percentile of your population's mean. That means that you are pretty close to the mean value, okay? If your z-score, let's say if your z-score is smaller than 1, let's go to a different color. If your z-score is between, it is bigger than 1 but smaller than 2, okay? Meaning that you are, okay, within this area, okay? That is called osteopenic. That means that you actually have a z-score that falls within that range, okay? So that means that you're osteopenic. So that means that you are in risk of osteoporosis. And if your z-score is bigger than 2, then you are in this range, and that means you are osteoporotic, right? How do we know this without even looking at the bone and just looking at the bone density? Well, because we have a very well established norms of who's osteoporotic and who's normal, and just by knowing this, by looking at the z-score of your bone density of one bone, we can figure out what everything looks like. Pretty interesting, huh? Okay, let's do an example before we talk about the sample statistics, so that will make it a little bit easier for you. So the example here is from your book. It's, I think, example 4.3 in chapter 4, okay? So it says that a true mean, okay, is 8.5 volts, okay? And then the true variance is 2.25 volts squared, okay? And it says it's a normal distribution, okay? And it asks if a single measurement is made, okay? Let's say xi, okay? What is the probability of this measurement value between 10 volts, okay, and 11.5 volts, okay? Okay, so from here, we can see the variation in the sample is going to be square root of 2.25, okay, and that's going to be 1.5 volts, okay? So the question is basically asking us that if this is a normal distribution, okay, this is 8.5 volts, right, because that's the mean. Let's say this is 10 volts, this is 11.5 volts. There's a probability of this being in this interval, so we'll call this probability of A, okay, and then we'll call this a probability of B, okay, and let's say this is A, this is B, and A, say 10 volts, and B is 11.5 volts, right? So what we are trying to figure out is that what is the probability of a measurement being in this area, right? In that case, it will be PB minus PA, okay? So to know that, we'll first look at the z-scores associated with the PA, right? Is going to be, let's call it ZA, and that's going to be 10 minus 8.5 divided by 1.5, okay? Remember that the z-score was defined as an interval, Zx, interval x, divided by the deviation, right? So that's going to be 1, okay? And then PB is going to be, say, ZB, okay? And that's going to be 11.5 minus 8.5 divided by 1.5, and that's going to be 2, okay? So we can look at the integral solutions from your table for either z equal 1 and z equal 2. This is table 4.3, okay? And you will find that PA is going to be 34.13%, and then the PB is going to be 47.72%, okay? The reason this is not 68 and this is not 95, PA and PB, because we are only looking for a one-sided integral, right? We are not looking at this part, we are only looking at the right side, therefore the values are half, okay? So then the probability of a PB minus PA is going to be 13.5%. So therefore, we can conclude that if I know what my central tendency and my variation, I can calculate what's the chances of a sample measurement being between two values. So that's the power of statistics if you had to access to the entire population. However, you don't have access to the entire population in most cases, right? Because as we said before, we only have access to small sample size and we don't have access to the entire population, right? So therefore, we're going to have to rely on something called finite sampling. Okay, sampling, and also assumed probability density. Assumed probability density. What I mean by that, okay? So if you have measured 20 measurements, right? Let's, as we did in our first example, and come up with a histogram like that, okay? And then, first of all, you're going to have to rely on your sample size. And second, you will assume that these samples follow a normal distribution. Okay? So this is your assumed distribution. Okay? And that is, oops, that is your histogram. Okay? So then your instead of your true mean value, right, you're going to have to deal with something called sample mean value, which is x bar, right? That is called sample mean, because that's just the mean of your samples, okay? And then the x bar is defined as 1 over n from I equal 1 to n xi. Okay, so that's the sample mean. Okay, your sample variance is going to be 1 over n minus 1 square, that's sample variance. Okay, then your standard deviation is going to be the square root of your sample variance. Okay, okay, and deviation between the mean and any given sample is then the xi minus x bar, right? And that's going to be deviation of sample of xi from mean. And I also like to define something called degrees of freedom, which is n minus 1. Okay, there we go. So this basically different sample statistic definitions replace our other definitions that we've been working with. Okay, so let's then define a couple things. Okay, so one data set is unknown. Okay, we don't know what x naught is. So this is now unknown, right? Because we don't have access to the entire data set, okay? But we can estimate what that true value might be lying at by, in our estimation, x bar is going to be x bar, that's the sample mean, plus minus a t value, which we'll get there, that's limited to z score, times my standard deviation. Okay, so this is my degrees of freedom, and that is my confidence level. Okay. Okay, so the t-value basically gives you a way to adjust your confidence interval. Okay, for example, if you want to say, I want to say my confidence interval, right, at 50th percentile, right? Let's say your sample size was 10, okay, and then your degrees of freedom is going to be 9. If you go to table 4.4, which is at the end of your notes, okay, that your t-value at 9 degrees of freedom and 50 confidence interval, okay, is going to be 0.7, okay, all three. In 95 percentile, okay, this value becomes 2.262, and at 99 percentile, this becomes 3.250. Okay, so what this means? So that means that if I want to say at this small 50th percentile, okay, with the 50% confidence, right, for example, the real mean, okay, true mean is going to be somewhere between x bar plus minus 0.7 times my standard deviation, right? So this is a small value, right? Because you are actually looking at a smaller value than your standard deviation. In this case, my confidence interval is going to become x bar plus minus 2.262 times Sx, right? That means that your interval get bigger, and then in the last one is going to be plus minus 3.250 times Sx. Basically, as your confidence interval increases, confidence level increases, the range that you state also increases, right? So, for example, I am 50% sure that the measured value, right, will be within 50% of the measured values will be, in this range. But if you want to say 95% of the measured values in a certain range, that you're going to have to increase the confidence level, right, or level. So that's why your t-value gets bigger, and then your t-value gets much larger at a 99th percentile. So this basically gives you a precision interval based on the probability level. Okay. Okay. So the last thing that I would like to define is something called standard error of means, or simply standard error. Okay, and that's defined as Sx bar, okay, Sx divided by square root of n. So the difference is there's a bar on top of x, okay? So then, using the standard error of means, we can define a confidence interval, okay? Meaning that x bar is going to be, x naught is going to be x bar plus minus a t value with certain degrees of freedom and confidence interval times Sx bar at certain confidence level. Okay, let's do an example. Okay, let's go back to the data table that we have. Okay, let me open that up. Data table in example 4.1. Okay, remember this. So we have our 20 measurements. Okay, so then we know that so this is example 4.1. So our sample size is 20. Okay, that means that our degrees of freedom is 19. Okay, and the question is what is, right, the confidence interval at 95 percentile. So in other words, what is the confidence interval at 95 percentile, right? So it tries to say is that find X bar plus minus TV 95, right, at SX bar 95 percentile. Okay, so let's do that. So our X bar is basically going to be average of all these samples. Okay, I've taken the average here using Excel, and then SX bar is then, you can do it this way too, 1 over 2, I equal 1 to 20, xi, and that's going to be 1.02. Okay, my Sx then, my standard deviation, okay, I have also done that. That's the standard deviation here, is going to be 1 over 19, okay, 1 to 20 xi minus x naught square, and that's going to be square root. Okay, and that's going to be 0.16. Okay, and my standard error then is going to be Sx bar. Okay, that's going to be Sx divided by square root of n, and that's going to be 0.16 divided by square root of 20, and that's going to be 0.04. Okay, then my xt value is T1995, so that's the degrees of freedom, and that's my confidence interval, and we do this from table 4.4. okay, and that value is 2.093. Therefore, my confidence interval is 1.02 plus minus 0.008 at 95 percentile. And therefore, you can define a confidence interval based on your sample statistics. And that's what you're going to do in your laboratory as well. And we'll talk about it this week. Thank you.